Right. Good evening, students. From continue from last week's class, we had covered at the ending of last week's session. We did digital electronics. If anybody can recall, we did digital electronics. Hello. Right. And in digital electronics, we covered electronic systems. We covered electronic systems, and the electronic system. Right. So, good evening, class. Once again, sorry for the delay with setting up the Zoom application. However, recap from last week's class, we said that we did digital electronics, and in the digital electronics, we would have covered something called electronic systems. We said that each electronic system comprised of an input sensor, a processor, and an output transducer. Anybody could give me an example of any electronic system that would comprise of all three components? Oh yeah, well, a typical example that I would have shared with the students, with you all, were that of a phone where you'd have your input sensor, which would have been like a touch screen, your processor, which would have been in the phone itself, and your output transducer, which would either have been your speakers or your monitor or your screen itself from the phone. We also spoke about two types of signal, and the two types of signal were analog and digital. And I said that analog signals are always continuous, that meaning that they were always going to be varying between zero to number and infinity. However, for digital signals, you only have two values. Two values were 0 and 1. 0 being low, as you see in the document there, and or off, and 1 being high or on. Everyone can see this document here that is posted on your shared screen. Good. All right, so and we started to dive into logic gates, and we said that logic gates, there are 5 types of logic gates, basic types of logic gates that we would be using. We talk about the NOT gate, the OR gate, the NOR gate, the AND gate, and the NAND gate. These 5 basic gates are the basic functions for any um, digital circuits. Why we need gates? Logic gates are basically electronic switches that perform a function based on arithmetic operations. So why we need these logic gates is basically for us, we would use it in these electronic system to perform function. Instead of us as humans being performing the function, this itself would perform the function for us. And logic gates often form the basis of microprocessors, transistors, and multiplexers. Microprocessors are the processors that we use in computer systems, phones, and other devices. We also include them into something called integrated circuits or IC chips. So when we go to purchase any of these logic gates, normally we purchase them as an IC chip, and the IC chip will help us to design a circuit that will switch in a particular operation. We start first with the NOT gate. We did this last week, the NOT gate, and we said that the NOT gate produces an inverted version of the input as its output. So basically, if you have an input here, whatever comes out going to be the opposite. This is the electronic symbol. For each of these gates, we'll be doing the electronic symbol, the Boolean expression, which is a mathematical expression that will calculate the output based on inputs, the electrical circuit that will help show the function of how it operates, and the truth table. The truth table basically gives you accuracy or tells you exactly how this gate operates. That's why we call it truth table. No matter how whatever the inputs be, it will always give the particular output. So let's start with the NOT gate first, the symbol. So the symbol is basically a triangle here with a bubble at the end, which means that whatever goes in, the opposite comes out. For example, your input is 0, your output going to be 1 here. The electrical circuit is the same electrical circuit as here. Let us consider this 0 as being the switch open or the switch not open. The switch open, sorry, and 1 meaning the lamp lights. So when the switch is open, current will flow in this direction here and the lamp will light. Alright? So which means that it is the opposite of the input. The input is 0, you switch open, but the lamp still lights. We take for example this second case here. In the truth table now, your input is 1. So obviously from the basic definition up here that we did first, the output have to be 0, but it have to be the opposite. But let's do it in terms of the electrical level in the circuit. So if here is 1, so 1 means the switch closed. So when the switch is closed, current going to flow through here and not to the lamp because it creates something called a short circuit. So the current going to flow through here and go back to the battery, creating a short circuit, and definitely the light itself would not, the lamp itself would not light. Hence, the output would be 0. Good. So the electrical circuit basically complements the truth table in that it gives you the exact output operations of it. An important thing to note, which I didn't include it here, but you can include in your lectures, is that this NOT gate is a single input and a single output gate, which means that you could only have one input on this side here and one output alone. All the gates we are going to deal with would have one output, but only the NOT gate will have one input. The other gates will have multiple inputs. Alright, so you can make a note of that the NOT gate only have one input and one output. Good. Any questions on the NOT gate so far? Good. Alright, well, seeing there's no questions, we'll move on to the next gate, which is the OR gate. Right, because we would have done NOT gate last week and we did OR gate as well. We'll go over the OR gate. So the OR gate, it produces a high output of 1, a high output of 1 if any of its input is high. So which means say once one of its input is 1, then it definitely going to get an output of 1. Your symbol for OR gate is this here. You need to know these symbols. All the IGC and CXC students, you will obviously need to know how to draw each of these gates, and you would need to know how to do a truth table as well as the Boolean expression. Not so much electrical circuit, however, the electrical circuit is just a complement the truth table. Right. So this is your electronic symbol. For it here, I want you to notice in the OR gate, you would have more than one input. So you could have up to 2, 3, 4. You could have multiple inputs. However, we just doing the basic, which is 2 inputs here and 1 output. You always have 1 output of a logic gate. However, you could have multiple inputs. Your Boolean expression is y is equals to a plus b, which means that a plus b is either, we consider it as a or b, but in math we know that plus means to add. So we'll see how this go along in the electrical circuit and truth table. So here, this is your electrical circuit, and this two switches are in parallel, which I would like to pay attention because other gates they would have them different. So the OR gate, the two switches, which is A and B, are in parallel. Your switches are your inputs, and your output is your lamps or a bulb, if you want to consider it that way. So we go in the truth table. So how we set up your truth table? Your first column is 2. Why we say 2 is because 2 is raised to the power 0, because this is the first column. 2 raised to the power 0 is 1. Your second column is going to be 2 raised to the power 1, which is 2. For your first column here, because 2 is raised to the power 0, the reason why we use base 2 is because of, we said here earlier in the very first part that digital circuits comprise of only two values, 0 and a 1. Good. So that's why we use base 2. So for base 2, raised to the power 0 is because of the first column here, and 2 raised to the power 1 is for the second column. For the third column, if you're going to use a third column, it's going to be 2 raised to the power 2, which is equals to 4. So you're going to have a 4 here. If you're going to have a next column, 2 raised to the power 0, 0 is 1. So that means you're going to have 1, 0, 1, 1, 1, 0, 1, 1. 2 raised to the power 1 is 2. So that means the first thing you're going to start with is two zeros, and then you're going to have two ones. Good? So So that's how we develop the truth table. So now we're dealing with the first conditions. When A and B is 0, which means that both A and B is open, what is going to be open? So current going to flow through the circuit here, but switch A and switch B is open. So that means no current going to flow through these two switches. So definitely the bulb is not going to light. We go with the second condition. If A is open and B is closed, which is 1, current will flow through in this direction. So current will flow through switch B, go through switch B and to the bulb, which will cause it to light, and back to the battery. So you would have an output of 1 once the lamp light. If switch A is 1, which means that switch A is closed and switch B is open, current will flow through switch A and to the lamp and back to the battery, which causes you to get an output of 1. For A and B, if both switches are closed in this situation here, A and B, current will flow to this point. However, both current will split up and still continue flowing after and cause the bulb to light, which means that you're going to have an output of 1. Now let us take this for example. If we go to use the Boolean in algebra, we're going to use, everybody seen this calculator that I have up?
Yes.
Good. Right. Let us use the first condition in the truth table. The first condition in the truth table is 0 plus 0. So remember from our Boolean algebra, we have y is equals to a plus b or a or b. So if you go to use 0 plus 0, your output going to be 0, which is what we have on the truth table here. Let me go with 0 and 1. 0 plus 1 equals to 1. It's the same thing. So again, as I was saying from earlier, for the OR gate, they said that your output is going to be high if any of its input is high. So once you see any of its input being 1, your output obviously going to be 1. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is supposed to be 2. But in binary, we do not have 2. We consider it as a 1. Good? So for the OR gate, once any of your input is high, all the inputs have 1 or any of the inputs have 1, your output is going to be 1. And these are the electronic circuit that shows you the same electrical circuit. However, the switches show you the configuration for the lamps. Any questions on the OR gate? Because we did this last week. So this is basically a short recap. Questions?
Rohit,
Yeah.
before you go on, guys, when you're coming on, please mute your mic unless you have a question or you're making a contribution to the class, please. Thanks.
Okay. Good. So, anyone have any questions on the OR gate? No?
Sir,
Good.
you could just go through back the August to table, please.
The OR gate, which one of the OR gate? The OR gate what?
To table.
Truth table. Okay, good. No problem. Right. So the truth table, because it have two inputs, your table will no longer carry 0 and 1, because as was shown from earlier, here your truth table would only have 2 raised to the power 0 because only one input you have. 2 raised to the power 0 is 1, so you're gonna have 1 0 and 1 1. However, because your OR gate have two inputs A and B, now you have two columns, 2 raised to the power 0 and 2 raised to the power 1. You're gonna have 1 0 1 1 1 0 1 1. Here you're gonna have two zeros because 2 raised to the power 1 is 2 and then two ones. Here we go with the first condition. So when here is 0 and here is 0, your output going to be 0. So the electrical circuit is the same electrical circuit, but however, the zeros means the switches are open. So if A and B is open, when current flows through the circuit, it cannot in no way cross these switches. So the light is going to be off. However, if you go to the second condition where A is open but B is closed, which is 1, yeah, current going to flow through the circuit through B, through the lamp, cause it to light and back to the battery. Good. Then you will have your inputs A and B for the third condition now. Your input A is 1, which means that 1 is closed. B is 0, which is open. So current going to flow through your circuit through A and cause the bulb to light again. However, now for the last condition, the fourth condition, when current flows through both A and B are closed, so current going to come through here and will pass through both A and B. The current going to split equally between A and B and then combine again and go through the bulb. We would have done a circuit like this about a week ago, something called parallel circuits, in which we know that the current splits for parallel circuits. So the current going to split up. However, they're still going to meet the bulb and cause the bulb to light at the end. Once the bulb lights, they all mean that your output is going to be 1. Good. If the electrical circuit is a little difficult, we could use the Boolean algebra, which is y is equals to a plus b. So we could use a calculator for that. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And 1 plus 1 should have been 2. But we do not have 2 in digital electronics. So we consider it as 1. So it's going to be 0, 1, 1, 1. And it also, the truth table also follows the conditions. The OR gate produces a high output if any of its input is high. For example, if your input, any of the inputs are high here in the first column, no. So because both of them is 0, your output is going to be 0. Here now the second row, because your input B is 1, your output is going to be Y. Because your input is 1 here, in the third row, your output is going to be 1. And because your input is both for both A and B is 1, your output is going to be 1 as well. Um, um, did this clarify any of your issues concerning the OR gate?
Yeah. Thanks.
Good. Yeah. So we're moving on now. So we'd have stopped at this last week class, the OR gate, and we'd have had one of these circuit. However, I did this notes and redo the notes so that I could be able to simplify for the students to understand for each condition. So we're moving on to a whole new gate now, which is the NOR gate. And the NOR gate produces a low output if any of its input is high. Now I wanted to go back now earlier to here. This it produces a high output if any of its input is high. So the NOR gate is basically the opposite to your OR gate in that once it have a high input here, your output is going to be 0. The traditional symbol we would have used for electronic circuit, electronic symbol for the NOR gate would have been the first one here, where you have a OR gate and then a NOT gate, which is a combination of both. However, these are two different gates would have had to use. So, so they would have designed the NOR gate by itself. And to design the NOR gate, they would have created the same gate. However, instead of using two gates, they created one specifically called a NOR gate. And you would just add a bubble at the end, which includes the NOR gate. That's the electronic symbol for it. Your Boolean expression is Y, which is the output, is equal to A or B, and this that line above it is considered, we call it bar. So we're going to say A or B bar, which means that it is the opposite. Once you use the bar condition, you're going to be opposite. So the opposite of A plus B. So if we go to use, for example, I'm going to show you here in the truth table, 0 plus 0. What is 0 plus 0? 0 plus 0 is 0. But what is the opposite of 0? Is 1. All right? Which means that it is the opposite of the original input output that you're supposed to get. For example, here you would have got 0 plus 0 is 0. But because it is a NOR gate and is the opposite of an OR gate, and because of this bar here, we will know that the opposite of 0 is 1. This is your electrical circuit. The electrical circuit is similar to this one. However, these switches are in series to the bulb. Even though they are in parallel to each other, this arrangement is in series to the bulb. When you are using the NOR gate, or the NOT gate, sorry, the NOT gate, as in this condition here, the same arrangement of the switches will now become in parallel to the light. All right. So let's go with the first row. 0 plus 0 is 1. So if both switches are open here, current will flow. It wouldn't go through the switches no more, but it will go directly to the bulb, causing it to light. So you will have an output of 1. However, let's go for a second condition. If your A is open, which is 0, and your B is closed, which is 1, so here is open, here goes current going to flow through here, go through B, and back to the battery, causing something called a short circuit. We'll talk about short circuit next week, but short circuit means that that's the shortest way that the current could pass through without going through any form of resistance. Alright, so the short circuit causes the bulb not to light. So your bulb obviously going to be 0. The same condition for the row 3, however, A will be closed. In fourth condition, which is 1 plus 1 and 1, which is 0, we just go through here. So when both switches A and B are closed, current going to flow. You're going to split up between A and B, however, you're going to join back here and continue back to the battery. No current is going to flow through the bulb, which means that your bulb is going to continue um, being off. So your output is going to be 0. If you're going to take a step back now using this here, this bar means opposite. A, so let me go. A plus B, which is 0 plus 0 is 1. What is the opposite of, I'm sorry, 0 plus 0 is 0. But the opposite, because of this bar here, we're going to say the opposite of 0 is what? 1. 0 plus 1 is 1. The opposite of 1 is 0. 1 plus 0 is 0, but the opposite of it is 0. 1 plus 0 is 1, but the opposite of it is 0. And 1 plus 1 is 1. We'd have learned that here, when the opposite of 1 is 0. This table is totally the opposite of the OR gate, which means that the NOR gate is the opposite for the OR gate. All right. Here you will see in the truth table, your layout is 1 0 0 0. For your OR gate, this is for your NOR gate. For your OR gate, now it's going to be opposite. It's going to be 0 1 1 1. All right. So the OR gate, to convert it into a NOR gate, you would have to use a NOT gate, and that's why we put the NOT gate here at the top here, and we would include a bubble. So if you are to draw a NOR gate in your exam, you are going to use this one. This was the traditional drawing before. We no longer use this, so we use this drawing, which is much simpler. Anybody have any questions with the NOR gate? Any questions with the NOR gate? Any questions on the NOR gate? Or need me to clarify anything about the NOR gate? Good. Nice. So we're going on to the AND gate now. So the fourth gate is something called the AND gate. An important thing to note is that the AND gate, it produces a high output if all the inputs are high, which means that both A and B must be 1 in order to get output of 1. Your electronic symbol for that is this symbol here, and this is the standardized symbol that we'll be using in the future. Your Boolean expression y is equals to A and B. This dot means in math to multiply. So that means that A multiplied by B going to give you the arithmetic output. So how we going to the electrical circuit for this is when A switch is in series with B switch and both of them is in series with the light. For example, let me use the math operation here, the Boolean expression. 0 multiplied by 0 is 0. 0 multiplied by 1 is what? 0. We're going to pull up the calculator so we go verify. So 0 multiply by 1 equals 0. We're going to do the same thing again. 1 multiplied by 0 is 0. And your third one is 1 multiplied by 1, which is 1. So if you notice here, even if you do not know how to do the electrical circuit and follow the electrical arrangement, you could use a mathematical expression, which is A multiplied by B. So A multiplied by B obviously going to help you follow the table, which also says that only when A and B is 1, then your output is going to be 1, which follows this statement. An AND gate produces a high output of 1 if all the inputs are high or 1. So all must be 1 in order for it to be 1. Let's use the electrical circuit now. We're going with the first row. For the first row, when A and B is 0, that means both switches are open. What is your output? So current going to flow through because switch A is open, no current going to flow.
So you was breaking up just now.
Oh, sorry. So as I was saying that the output of the circuit here going to be 0 because for the first row, when current flows through A, because switch A is open, no current going to go through. So your light definitely, the bulb didn't definitely not going to light. So your output is going to be 0. Let's go now with the second row. For the second row, A is 0. That means A is open but B is closed. So your closed switch B here, current going to flow through the circuit, but it cannot pass A. So that means no current going to flow through the circuit anymore here. So your light is not going to, your bulb is not going to light anymore. So you're going to be 0. Now if input A is closed and B, switch B is 0, as in here, your switch is closed at A, so current going to flow through A, but because B is open, no current could flow through B, so definitely a bulb is not going to light anymore. Going to light at all. Sorry. So your output is going to be 0. And for your last here, which is the fourth row, if switch A and switch B is 1, both of them is closed, current going to flow through switch A, flow through switch B and to the bulb causing it to light. Right, and I get an input of 1. So you can use the electrical circuit to create the truth table or the Boolean expression, which is a mathematical way to create the truth table. Whichever way you feel comfortable using, you can use. Any questions on the gate. Any questions on the AND gate? Okay, good. All right, nice. So we're moving on now. So that was the AND gate, and now we're moving on to the NAND gate. An important thing to note about these gates is that once it is considered as the opposite of the gate, normally have an N at the front. For example, your OR gate here, scrolling back to your OR gate. So this is your OR gate here. However, the opposite of the NOR gate, the opposite of the OR gate is a NOR gate. This N symbolizes that it have a NOT gate in front of the OR gate, the output of the OR gate, which means that same thing for the AND gate. This is your AND gate, and if we are going to deal with a NAND gate, which is the opposite of an AND gate, you're going to have a NOT sign, and this is your NOT symbol. This again is a traditional symbol we used to use, where we would have two gates to make up one. However, now we are using only one gate, and the second gate is what we are going to draw for the electronic symbol. So NAND gate produces a high output if any of its input is low, right? Your Boolean expression is as follows. Y is equals to A and B bar, which means that once the output of it is the opposite of the output, sorry. So if A and B, so 0 multiplied by 0 is 0, the opposite of 0 is 1. That's why we get this condition here. All right. This is your electrical circuit for it. I would like you to pay attention. These two switches in the AND gate were in series before in the AND gate, but because now it is a NAND gate, these two switches were in series in the AND gate here. However, in the NAND gate, they are still in series, but however, they are placed in parallel to the bulb now. Both of them was in series to the bulb in the AND gate, as here. However, because it is a NAND gate, it is now in parallel to the bulb. We go with the first layout. So we go in with the Boolean algebra. So we go with the Boolean part. So here we do the maths part. This bar means opposite. So 0 multiplied by 0 is 0. The opposite of 0 is 1. 0 multiplied by 1 is 0. The opposite of 0 is 1. 1 multiplied by 0 is 0. The opposite of 0, because of this bar here, the opposite of 0 is 1. And 1 multiplied by 1 is 1. Well, would have, well, 1 multiplied by 1 is 1. And the opposite of 1 is 0. So that's using the maths part, you could create the truth table. However, with the same thing with the electrical circuit. Here, if both switches are open in this scenario, current going to flow through, bypass these switches and go directly to the bulb and cause it to light. So that means once the bulb lights, both switches are open here in this case, current going to flow, causing the bulb to light. So you get a condition of 1. If A is 0, if A is 0 and B is 1, so we say A is 0. Well, actually I have it wrong side. Oh, B A is 1 and B is 0. So A is closed, B is open. So current will flow. Because it have no way for the current to flow here, it goes directly to the lamp and causes the bulb to light again. So you get a condition of 1, the bulb lights. The fourth row, you would have the two switches now closed, A and B closed. So when A and B is closed, current going to flow through A and B, creating something called a short circuit. This would cause the bulb not to light, so definitely your output is going to be 0 here. To remember, the NAND gate is the opposite of the AND gate. Your NOR gate is the opposite to the OR gate, and your NOT gate basically gives you the opposite of whatever comes in. Those are the 5 basic gates that we need to know in order to create any electronic system. There are plenty others. For example, when you're going to do higher physics, which is form 6, you would need to know the XOR gate, the XNOR gate, and so forth. There are four others again you need to know. But at this level, we are only to learn these 5 gates. So any question on the NAND gate? Any question on the NAND gate? Or any gate in particular? Anyone? Okay, good. All right. So a request to recap this gate, which is the NAND gate. Right. So for the NAND gate here, the NAND gate produces a high output, which is 1, when any of its input is 0. Simple. So we would only have the outputs of 1 when any of its input is 0. So we look to see which input is 0 here. So for here, condition B is 0, A is 0. So both switches are 0, so you're going to have an output of 1. Where is a 0 again? Second row. A is a 0. The output is going to be 1. B is a 0. In the third row, the output is going to be 1. Any of A and B in the fourth row is 0. No, both of them is 1. So you're going to be the opposite, which is a 0. The gate that you are going to study for exam is this one here, which is a NOT gate. You're going to draw AND gate. Just you're going to include a bubble. This bubble means that is the opposite of an AND gate. Your Boolean algebra is y is equal to a multiplied by b, the opposite of that. That's why we have something called a bar here. So, for example, 0 multiplied by 0 is 0. The opposite, because of this bar here, we're going to use it as the opposite. The opposite of 0 is 1. 0 multiplied by 1 is 0. The opposite of 0 is 1. 1 multiplied by 0. The opposite of that is 1. So 1 by 0 is 0. The opposite of 0 is 1 here. 1 multiplied by 1 is 1. The opposite of 1 is 0. You could use this Boolean expression to create the truth table if you wish, or you could use the electrical circuit in which both switches which are in series each other are now in parallel because of this NOT gate here. All right. Once they're in parallel, the arrangement looks like this here. So for the first condition, if switch A and B is 0, which means that both of them is open, current will flow through the circuit, go directly to the bulb, causing it to light. Once the bulb lights, the output is going to be 1. Third row, if A is 1 and B is 0, so A closes, now B is open, current cannot go through A, so that means current will continue going to the bulb and back to the battery, which means that your bulb will light. So you have an output of 1. However, now for the last condition, which is the fourth row, when A is 1 and B is 1, which means that both switches are closed here, A and B is closed, current going to flow through switch A, through switch B, and back to the battery, creating a short circuit. This will cause obviously the bulb not to light, causing an output of 0. So whichever method you choose to use, if it's the Boolean expression or the electrical circuit, whichever way, your output's going to create this truth table here, which would follow the conditions. Any questions? I hope that helped. For the recap on the NAND gate, Dylan, did this recap help? Good, nice. So, obviously we'll take a break as usual. So, um, the next thing we're gonna start. So we'll take a break from around 6 to 20 past 6. But before, I just want to touch on logic gate control system. So logic gates, this is what we're going to deal with. These are how we're going to integrate the logic circuits into any machine operation or any security system or any system, as a matter of fact, once it have an electronic circuitry in it, we are going to use gates, logic gates. So logic gate control system. Logic gates used as microprocessors in electronic control system. So basically, as was explained earlier, we use them for three different things, three basic different things, for transistors, multiplexers. We use them for transistors, for multiplexers, and for microprocessors. The most important one is the microprocessor because microprocessor is where the programming takes place, all the arithmetic operation takes place in any electronic system. For security system, for example, you would have a push switch, a NOT gate, and a bell. So this is a simple alarm circuit which would say that when you push the button here, your NAND gate is going to come on, which means that the bell is going to come on. As a security system, if anything break in or anybody break in the building, you just use the security or the fire alarm or any alarm bulb alarm switch that will trigger the bulb. So you would have an input sensor here, your processor, and your output transistor. This was explained at the very beginning of class last week. Just going back to recap, all electronic systems comprise of three basic things: your input sensor, your processor, and your output transistor. As was seen with your cell phone, it's the same thing with your cell phone or your laptop. Like take for example your laptop. Your input sensor, your input will be keyboards. Your processor, obviously, you're going to be whichever type of processor you use. If you use Intel, AMD, and so forth, and your output transistor or your output going to be a monitor, your speakers, or any other output device. Similar here, your output device is your bell because you could actually hear it. Your processor would be the gate, and your input sensor would be a push switch in this scenario. Good. So anyone of the conditions, they will operate. There are three others that we're going to be dealing with, which is the safety system for machine operations, the heater control system, and the lights. We deal with that. Resume class. So we're gonna break and coming back for 20 past 6. I will be here 20 past 6. Um, so 6:20 we resume, alright? Do not disconnect, please, because classes as usual. You're just gonna drink a coffee or take a water break. Good. So I'm see you back in 20 minutes time to continue. I would have posted on the group chat for you past papers for IGCE and CXC. And we do the same routine, which is after the lecture we would do some past papers on IGC and some on CXC. Good. So see you back in next 20 minutes. Do not disconnect and enjoy the break. I want to enjoy mine as well. All right. If any question arise, keep it in mind as we resume 6:20. I will take the questions and try to clarify them as soon as possible. Okay. Enjoy the break. Good day, everyone. Resuming from our break. I hope that everyone there at the moment. I'm ready to continue. Everyone here? Good. Good. So just continuing, the last where we stopped at was the logic control system, and the simplest of one we did was the security system, in which we'd have a push sensor, which would bring a push button, and you're not get to relay the information to bell. But there's a timer, so obviously the NOT gate would include a timer that would cause the bell to ring a certain time. Your bell is your output transducer, NOT gate is your processor, and your input sensor would be the bell push. Similar for the safety system here, you have switch A and switch B, an AND gate, and a motor. For example, if for any safety systems, normally there would be two um two devices that you would need to interlock with each other in order for the motor to operate, right? Which would mean that switch A, we consider as switch A, which would be a normal start button. However, there may be in some scenarios a guard that would have to move, as in lights. Most of the time, in lights, you would have to move a guard, even though the motor is running. You need to move a guard in order for the blades to operate. So that means that both switches, which would have been this push button or the start button, sorry, and the guard, and both of them would have to be on in order for the motor itself to come on. And that's a function of the AND gate, because 1 and 1 will give you an output of 1 for the motor to come on. Lower down for the heater control system, you would have a temperature sensor and a light sensor in this scenario. The sensor is obviously going to give you adjustment for the heat control. The heater control system that we are talking about here is not a water heater, mind you. It is the system that they use where it would be to keep the room at a particular temperature. We use the same systems in the eco-friendly air conditioned units, in which they have sensors that would automatically sense the temperature of the room and would make the various adjustments to control the heat or the coolness in the room. For the lights, it's similar here. Um, this light system, we use it mainly for stadiums and so forth, in which you would have a normal switch, but then you would have a switch to override it, which which means that either you could switch on the lights using the normal switch, or you wait for when the place get dark and then the lights will come on. So either way, because of the OR gate, either use the normal switch for it to come on, or you use the photo sensor for it to come on. So that's where we use the OR gate in this light system. So just like the street lights, there is in most stadiums there is a panel in which you would have a light switch to put on the lights anytime you want. However, if you wish for it to come on a particular time when the place is dark, there is a sensor that would trigger it to come on. So either way, the light's gonna come on. However, it be whether you put on the manual switch or you use the photo sensor. So all of these are like the AND gates and the NOR gate operation, showing how we implement the gates in streetlights. Good. Any questions concerning how we use the gates in the control systems? Any questions? Good. All right, nice. So we're going to go on to do past papers now. So we'll look through some past paper questions. Because logic gate was a big part in CXC. It does play a particular role in CXC, but however, it is not that dominant anymore in CXC and IGC. However, they do show up from time to time. So in case they do show up, because it is on both syllabus, you would need to cover it. For CXC, it did play a predominant role in during the years of 2005 to around 2013 or 14, um, before the syllabus slightly changed, which included many other things. However, IGC, it did play a role between 15 to 18. Slight changes, however, it will show up now and well, now and then. Good, so we're going on for the CXC students. Well, let's see. Alright, we could do this. Yeah. Alright, we do the IGC first, and then the CXC. So this is your IGC. For the IGC students, there is a document attached to your WhatsApp group chat, or you can see it here as well. These are the past papers over the years that all the digital electronic question. Yes, I actually did send the notes on the group chat via WhatsApp, but I could do it again. So you all could see it, even though I have a shared screen. I'll still send it on the group chat, but I think I did actually send it on the group chat. Uh, yeah. Well, I will send it back so that you all could see the. Okay, good. I'm just gonna resend it for those who haven't seen the documents posted. However, it would be on my screen share, but the actual document itself is on the group chat. But I would resend them again so that you will get access to it. Um, you could print it at home and do the working as while I go through them here as well. So we're gonna deal with the IGC students. So we worked on some past papers firstly, so that we would get a hang of how to do these past papers. So, good. So everyone seen this? Uh-huh. Everyone seen this pin document? Good. Right, so this is the past paper question. I had to do it in this way so I could get to use the cursor to follow the answers. So this came out from which year? Let me see if I can get it. Came out from actually from 2016. This was an electronic question. The first part of question 10A part 1 says figure 10.1, which is this symbol here. I would have given you a document 2 weeks ago about some components and symbols. Show the symbol of a circuit component. Name the component. So they say which component this represents. Anybody have any idea? Something is blocking it. So I'm gonna close off some applications. See it now? Oh, I can't see the pin document. Okay. All right. Well, we'll just work it from here. You all see the PDF as usual, right? Good. All right. So for here, the symbol here is what? This was the symbol that was given. We would have done this, which would have been a LED. So this would have been an LED. Should have been your answer here. And LED stands for light emitting diode. So let's see if I could fill it out here. So fill and sign. All right, well, let's see, right? So it's a light emitting, also known as LED. You would have known that because most of the time it's all of our components that we buy now, as well as I urge all students to use LEDs, bulb, save money. Alright, so that's our light emitting diode. I'll see the solutions there while I do it. Let me share the screen. Everybody get to view the LED that I just wrote the name of the component. Yeah, good. Alright. In the space below, draw the symbol of a NOT gate. How we draw any symbol of a NOT? Well, I cannot draw a NOT gate here. However, I could show you what the NOT gate is, and you could complete it. Which your NOT gate would look like this. Um, let's see if I can. Oh, I forget I have I actually have uh, right. So your NOT gate, right? Your NOT gate looks like this here. From the notes, we toggling between the notes and the desk thing. So your NOT gate looks like this here. So this is the symbol you need to use. So your NOT gate going to look like this here. So your answer. Oh, I can't even draw anything here. So your NOT gate should be placed between here, right? And it should look like this. So let's see in this snipping tool that I just cut out the NOT gate. So this is your NOT gate here. Sorry. For the questions, so you just include that for your answer. Going lower down. 10b, which is says figure 10.2 shows a digital circuit A, B, C. So this is what type of gate again? Anybody knows what type of gate this is? You can type it in the chat so I can know you're following. Anyone knows? AND gate, yes. So it is an AND gate. And this one here, the second gate here. Which gate it is? Anyone? OR gate. Yes, good. So this is your AND gate here, Jenna, and your OR gate here. So you're good. Excellent, David. So your OR gate means, if we go back to the file, your OR gate. So if we go and see what the conditions are for the both the AND and the OR. So your OR gate, what is about the OR gate? Produces a high output if any of its input is high. So once your input is 1, your output going to be 1. And for your AND gate, let's go down to the AND gate. They say that the AND gate produces a high output if all the inputs are high, but all must be high. So we go back to the worksheet here. The question here says complete the truth table. So output of C. So between A and B, you get an output of C. So this is your AND gate here. So 0 and 0 is how much? 0. Good. We go again. 0 and 0 is 0. 0 and 1 is, remember for the AND gate, it come like a multiplying. So 0 multiplied by 1 is 0. Good. 0 multiplied by 1 is 0. 1 multiplied by 0 is 0. 1 multiplied by 0 is 0. 1 multiplied by 1 is 1, because in an AND gate the function is it must be multiplied, right? So if we use the mathematical function, 1 multiplied by 1 is 1. So the output of the AND gate means you're multiplying because it's the output of C. So A and B, so we're going with A and B. 0 by 0 is 0. Once your inputs are all 0 or any one of them is 0 is followed, you're completely, the output has been 0. So simple thing to note, you match these zeros. The first four is 0 here, you put 0 here, 0, 0, 0, 0. The second two is 0 here, you put 0, 0. Now you watch here, all four of these are ones, so you put two ones here, one in this row and one in this row. Everybody okay with output C so far? How we complete the table? Good, excellent. So we're moving on to now to output E. Output E is OR. And if we go back to the file now, we said that in an OR gate, what we say? OR gate produces a high output if any of its input is high. So mind you, once any of the input is 1, the output going to be 1. So for the OR gate, we go back. So once the input is 1, and that OR gate comes from what? C and D. See two conditions, C and D here. So we're dealing with these two columns here, output C here and output D. So once the output has 1, we go back to the OR gate. The condition you have to add them. So A or B. So add. Going back to additions. So 0 add 0 is what? 0. Good. 0 add 1 is 1. 0 add 0 is 0. 0 add 1 is 1. 0 add 0 is 0. 0 add 1 is 1. 1 add 0 is 1. And 1 add 1 is 1. Alright, so we follow in the truth table of the OR gate, which means that once any of the input has a 1, the output is going to be 1. It's the same thing here. You have a 1 here, your output is 1. You have a 1 here, your output is 1. You have a 1 here, your output is 1. For 1 here, your output is 1. And you have two ones here, so your output is 1. Everyone okay with working out output E? How we get the answer? Good. Excellent. So we're moving on to part C of the question now. So part C of the question here says, suggest a modification to the circuit in figure 10.2 to produce the output Z in the truth table. The output Z in the truth table. Alright, to produce the output Z in the truth table below. It may help you to compare this truth table and the truth table in B. So what we need to do, we need to figure out which one of these is going to give us an output of thing here. But I wanted to notice now, our three inputs from here are what? A, B, and D. They want one modification that could assist you to get all these outputs being a 1. So here I'll put A and B and D is 0. A and B is 0 and D is 1. Still have a 0. So if you watch here, output Z is this here, which means that which gate we're going to include to give our output in which all are ones. Which gate we're going to use to get 1, 1, 1 here. Which gate you think we're going to use to get this output? Hmm? For here. Instead of using, so let me just think about it. So using the circuit, but how we can modify the circuit here, this whole thing in order to get the values that we want. We want the values at z. Z would now become where E is, but we're going to change up this whole thing here. How we going to do that? We could use something called an AND gate. Look at it. For the AND gate, what we say about the AND gate, all the inputs must be 1, where output are 1. So we could distinctly see here, use an AND gate for the inputs of A, B, and D. Good, that's your three inputs, A, B, and D. And if you notice here, these are three input. You could use it use an AND gate at three. Sorry, should have been a three input AND gate. Use a use an use a three input AND gate for the inputs of A and B. Then what are we going to use three inputs? Here's 2 to the power 0 is 1, so you got 1 0 1 1 1 0 1 1 1 0 1 1. Here is 2 to the power 1, which is two zeros, then two ones. 2 to the power 2 is 4. 4 zeros, 4 ones. As we were seeing when I was doing lecture. So this whole thing here, we could use a three input AND gate. A three input AND gate would have A, B, and D in it, and one output of Z. That your AND gate always gives you output of one output. Sorry. Let me see if I could draw this in paint and just take up it here for you all. Um, Wow, clearly that didn't work. Let's see if I can switch it. Three input AND gate. Anybody see the Google screen that I have? No? Good. So hello? Alright. Let's see this Word document here. Hmm? Everybody seen this Word document? Nope. Okay. Well, your three input AND gate would you could search a three input AND gate. I'm gonna actually send you one on the group chat for you to see. Huh?
Yes. Am I on?
Good. Um, so I'll send it on the group chat the three input AND gates. So you'll see however they use WXY. We are not going to use WXY, we're going to use ABD in ours. Um, and the truth table is the same, so you could go through it. That's the truth table, the same exact truth table that we have here as our answer. Good. So hope everybody get to see the three input AND gate that we have there that I posted on the group chat. All right. For these IGC students, maybe I could try working on this one by the time number 6. just this page here while I work on CXC. But we could all do it together. It doesn't matter because we'll get practice anyways for both. Good, so we will both work on each other documents so we'd have an idea. Alright, so for the CXC people, if you're following up, and most of the IGC if you're following, even better. Question 5 just came from a past paper, which is 2005. The question here says, identify the logic gate. Identify the logic gates described in the first column of the table below, and hence complete the table by writing in the names and the logic symbols in the appropriate columns. So let me go first to the first one. So they said here, the output is always low except when both inputs are high. Which gate you think this is? So only when both the inputs are high, then your your input is going to be high in essence. So they say both output is low, always low except when both inputs are high. Which gate? There are 5 gates. There is not. So they talk about inputs. So definitely we cannot be talking about NOT gate because NOT gate only have one input. However, which means we have to choose from the AND, NAND, the OR, and the NOR gate. So we are saying the output is always low except when both inputs are high. Which gate have for both inputs are high? Let me scroll through here. So we starting with the OR gate. The both inputs are high, but the question they really asked was output is always low except when both inputs are high. So here it have both inputs are high, but all the other times is still high, so that we cannot use that same thing with the NOR gates. We go into the AND. We go to the AND now, which is here the question says, we go back to the question. Um, output is always low except when both inputs are high. So we go into the both. So output is low, which is all the inputs are low except when both of them is high. So your answer should be for this one here, should be for the first one in this column here, AND gate. So this should be an AND gate. The name should be AND gate, and the symbol for AND gate is as shown here. You have to draw this symbol here. And for the CXC people, once you have it completed on the page, please, if you have it printed, because I didn't print mine. For we go to the second one now. So everybody okay with that so far? Hmm? Everyone okay with this first column so far? Being AND gate and the symbol for AND gate, especially the C6 student. Good. Right. So the output now, the second column, the output is always high except when both inputs are low. So the output is always high except when both inputs are low. So the both inputs have to be low. Wait. The output is always high except when both inputs are low. So we are saying that only when the two inputs are 0, then your output going to be 0. So both inputs must be 0. Your input is always high except when both inputs are low. So we're looking for both inputs. So for both inputs are low here, so you get a 0. And all the other times it exists as a 1. So this gate here is an OR gate. So the second answer is an OR gate. You're going to include the name of it, the OR gate, and the symbol. This is your symbol for OR gate here. So you can draw any symbol for OR gate here from CXC students. Alright. So we're going again to run. Everybody okay with this second row, right? Understanding it? Anyone? We're moving on. Alright, the output is always high except the output is always high except when both inputs are high. So what we are saying here, when both inputs are high, the output is going to be low. Both inputs are high, so when both of them is 1, your output is going to be 0. Then definitely that follows this arrangement here, which is your NAND gate. So let's go back again. Output is always high, which is here, always 1, except when both inputs are high, which is 1. So your answer for this third row would be a NAND gate. So your answer should be NAND gate here, and the symbol for NAND gate is shown in the diagram here. We're using the second one, alright? The second diagram. So everyone, well, most of the C-Sec students, you all completed that. I'm not hearing from the C-Sec students. Good, excellent. So we complete the table. Your first answer is the AND gate. Second answer is the OR gate. Your third answer is a NAND gate. Good. So we're going on to figure 2. Shows a logic circuit. So you have a logic circuit. You have an input of A goes into X and B goes into X as well. But A now goes into a NOT gate and it goes to becomes W and it goes to your other gate, and B goes to this gate. The output is X and Y. These two types of gates are what type of gates again? What gates are they? Anybody? Both of them is the same thing. What type of gates are these? Anyone? Good, AND gates. Excellent. So we deal with AND gates. So firstly, we're going to deal with this condition here. This one here is this is W. Sorry, we're going to deal with W here. And W means that A goes in through a NOT gate and then it comes out the opposite to be W. Right? So W basically is the opposite of A. So we're going to complete this table here. So the opposite of the opposite of 0 is 1. The opposite of 0 in this case is 1. The opposite of 1 is 0. And the opposite of 0 is 1 is 0. So that's W. Everybody see so far. So W comes from what? The opposite of A. Anything that goes into and not get the output is the opposite. So if A goes in with a 0, output is going to be 1. If A goes in with a 0, output is going to be a 1. Same thing here. 1 goes into a 1, your output is 0. 1, your output is a 0. Let's go with X now. X means that it is A and B because A goes in here to the AND gate. B as well goes in to the gate. So X is A and B, which means and means to multiply, right? So 0 multiplied by 0 is 0. We use in the maths way. 0 multiplied by 1 is 0. 1 multiplied by 0 is 0. And 1 multiplied by 0 is 0. So all your answers for this here is 0. Because in the AND gate, you would need the two inputs to be 1 in order for the output to be 1. Okay? Everybody okay with solving for W and X so far? Huh? Everyone okay with W and X so far? Solving W and X? Good. Nice. So we're moving on to Y now. So we're going with Y. Y comes from what? B and from W. You see the W here? So our two to get Y is W B and W, B multiplied by W. That's how we're going to get Y. So we're using the two columns. That's this one here, this whole column here, column 2, and then column 3. That's what we're going to use. So 0 multiplied by 1 is 0. 1 multiplied by 1 is 1. 0 multiplied by 0 is 0. And 0 multiplied by 0 is 0. So your truth table is completed with it being 0, 1, 0, 0. Good, everybody okay with solving for Y now? Most of the C-Sec students, yeah, good. Alright, so we're moving on lower down now. So for the C-Sec students, we still continue the past paper. Here, they say the logic circuit of figure 2 is incorporated in an electrical system of a car. So mind you, we would have done logic circuit control system, we would have done for a heater control system, a safety system, a lighting system, and a machine operating system. Now they're doing it for a car. What I said, the logic circuit of figure 2 is incorporated into the electrical system of a car as shown in figure 3. That's this system here of switches S1 and S2 are operated according to the table below. So 0 means what? To open, and 1 means to close. Good? So we're looking at the conditions here. So open, so we have two doors here. S1 and S2 are doors that operate or switches. So we are seeing here now from this circuit, your alarm will come on from A and from B. Seen it? So alarm 1 would come on from A and B. So both of them must be on for alarm 1 to come on. For alarm 2 now, for S1 and S for alarm 2 to come on, S1 and S2, S1 must be off and S2 must be on. Why S1 must be off is because the passenger are not gate. So once it off, it's going to becomes a 1. So it's going to be a 1 at W, and for B, when switch B closes, it's going to be a 1. So only then alarm 2 would come off. Come on. So switch 1 on, engine off, door open any state, close door any state, switch any state, switch to any state, on, off. They say explain what happen if the door is open and engine is off. So the door is open, so we're looking for door is open here, good, and the engine is off. So the door is open and engine is off. So the door is open, alright, and the engine is off. So the engine is off here. Let's see if I see highlight. So alright, so if so we're going back to here. So when the engine is off, that's here. So right. So your engine is off here. Good. And the next condition is that the door is open. They are asking here, explain what happens if the door is open and the engine is off. What's going to happen to switch 1? Switch 1 is going to be off, and switch 2 going to be what? Any state for the engine to be off and on for the door to open. So the door must be open. So the door must be open and the engine must be off. So your switch 1 must be off and your switch, so definitely your switch 1 must be off and your, so here your switch 1, explain what happens if, so switch 1 going to be what? Going to be off and switch 2, what going to happen to switch 2? Switch 2 and switch 2 going to be on. Good. So for the engine to be off here from the from the table, switch 1 must be off and switch 2 must be on. Good. Everybody understand that part so far? Because covered label on the table. Everybody okay with figuring out which switch is going to be on and which switch is going to be off? Then, so the door is open. Let me go to the next part now. The door is open and so the door is open and the engine is on. Let's see. So we're gonna remove this one here. Delete that. So your door is open and the engine is on now. So the engine is on. So good. So we're going with engine on and door is open. What's going to happen to switch 1? So switch 1, it must be on for the engine to be on, and it could be any state for the door to be open. So switch 1, so switch 1 on, switch 1 on and switch 2, what happens is switch 2 now. Switch 2 must be on as well for the engine to be on as well and the door to be open. So switch 2 must be on. Everyone see that from the table here? Any state means you could choose any state. So that's the reason why we just look at the state that causes the door to be open. For example, switch 1. Switch 1, it must be on. If it off, it doesn't matter for the door going to be open always. However, for switch 2 now, for the door to be open, it must be on. So we use the on from the engine here, which switch 1 must be on at all times and switch 2 must be on in order for the engine to be on and the door to open. Everyone okay with that? How we solved that part so far for the C-second particular? Good, nice. So we'll move on for the C-sec students. You are going to work this one here by the time. Um, we will go through this in a bit. For the IGC students, pay attention. We're going to work this one here. So we're going to do second past paper question. Okay, the second past paper question is as follows. It said figure 10.1 shows right, figure 10.1 shows a digital logic circuit not using the recognized symbols. Again, so we don't know the symbol, but we know it is an AND gate, just like how I had shown in the merge file. Sorry, not the merge file, our lecture, where here they didn't show the exact gate, but it just used a square box and it put OR gate in it. Same similar for this one here. This is an AND gate, this is an OR gate. For AND, the both input must be 1 in order for the output to be 1. They ask us now in this table here, complete the table below to indicate the logic levels of points D and E in the circuit when A, B, and C are the logic level indicated. 0 represents low or off, 1 represents high or on, just as we did in our lecture. Um, so we're going again. So this is an AND gate. Condition for the AND gate. We say that the AND gate, for the AND gate, your output produces a high output if all the inputs are high. So we're going back now for the IGC student. Between A and B here, because your output is D, we're dealing with D here. Your output is D. So D, for D, your output is D. D between A and B. So between A and B, which one is 1 here? This row. So you're going to be 1 for this row here. Every other row going to be 0 because the other inputs are 0. See that? A and B is 1. Both inputs must be 1 in order for the output to be 1 because it is an AND gate. Everybody else is 0, so you put 0 here. As for D, we're going to do E. Point E is here. This is complete the table below to indicate the logic points at D or E circuit when C are at the logic levels in the. What is going to always C? Okay. C would be 0, 1, 0. Because the first column any inputs, we're going to classify first column, so it will be 2 to the power 0, which is 1 0 1 1 1 0 1 1. I continue like that. Part E now, they said the logic is an OR gate. Your OR gate means that if we go back, so your OR gate says that produces a high output if any of the inputs is high. So once you have a high input, your output is going to be high. That's the OR gate, so we're going back here. So where between C and what? C and D, you're going to get output of E here. So between C and D, you're going to have an input of 1 here, 1 here. Everybody else is 0. Good, so that's the output. Draw a recognized symbol for the AND gate. So we have to draw an AND gate. Your AND gate looks like this. So oh noise AND. So your AND gate looks like this. For this diagram here, you put it in here. Your AND gate. So everybody good so far up till part B. IGC students. How we complete the table and draw the AND gate. Good. So we're going on to the NAND gate now. Part C of the question. They said the NAND gate can be replaced by an AND gate and a NOT gate, which is, let me just scroll along a little bit. I did see that in my lecture that your NAND gate, which is this, can replace an AND gate and a NOT gate. That's exactly what I said here. So they say draw a label diagram to show how the AND gate and the NOT gate should be connected. Label clearly the logic gates and any input and output. So basically you are drawing this symbol here with an AND gate and a NOT gate connected to give your output. So this is the symbol they're asking you to draw. The top one, which is the traditional one, the traditional symbol that we used to use before. Right, so for that you are using an AND gate and a NOT gate to produce a NAND gate, and it comes directly from the lecture here. Good. So take down that and we will continue. All right. So everybody okay with this part so far? Up till this point here, part C. Any questions? Any questions so far concerning the passive part? Good. I hope everyone doing the passive part, by the way. All right, so we're moving on now. We'll do one more question in the IGC before we continue with CSEC again. However, IGC, CSEC students could follow and IGC could do the same thing for CSEC. Right, so we're going on with the third page, the fourth page actually, sorry. The question here says in number 7, 10, 10.1 is the symbol of a NAND gate. All right, you have two inputs A and B set out. One input A and input B can be set to 1 being high, 0 being low, or 1 being on, 0 being off. Complete the table below to give the outputs of this NAND gate. Let me go back. What a NAND gate is, it produces a high output if any of its input is low. So once your input is 0, your output is going to be 1. So here the two of them is 0. You have a 0 here. So you're going to be at 1. You have a 0 here. You're going to be at 1. Both of them is zeros. Both of them is 1 in the fourth row. So your output going to be 0. Everybody see how we do that? And if we go back to the truth table, it's the same exact thing. From like a 1, 1, 1, 0. Yeah. All we did was just look for weight of the zeros. We put in a 1. Anywhere we had a zeros in the both columns, we put in a 1 to the output. And then you check to see everything else is going to be 0 in this scenario. Everybody okay with this part here? Or recap it? Everyone okay? Okay, good. Well, everybody's pretty good so far who reply. Nice. So we're going on to part B of the question now. The the two inputs of the NAND gate are joined together. So you have two inputs, which means that if your input is 0, that means you're going to have a 0 coming in here and a 0 coming in here. Are connected to input C as shown. Determine the output of this NAND gate when the input C is set to 0. So you're coming in with two zeros. What happens to the NAND gate? Let me go back with the NAND gate. Let me see if we understand the NAND gate. The NAND gate says produces an output of 1 if any of its input is 0. So if your input is 0 here, your output going to be 1. And for your input here, if your input is 1, your output going to be 0. Because both of them going to be 1. And it's similar. Both of the inputs are 1, which is 0. And any of the zeros going to give the input of 1. That's for the NAND gate. Everybody okay with that so far? Again, it's a name the logic gate that behaves in the same way as the NAND gate in figure 10.2. 10.2. As this here is a name the logic gate that behaves in the same way as a NAND gate in 10.2. Right, now we go back. So notice here the question they had asked was state the name of the logic gate that behaves in the same way as the NAND gate in 10.2. So 10.2 we are saying is when the input is both of them is 0, your output is going to be 1. When both of them is 1, your output is going to be 0. So we're going to look for a NAND gate, a gate that's going to give you when both zeros, when both inputs are 0, you're going to be a 1. And so here, and when you have both ones, you're going to be a 0. So one similar to that is your NOR gate, which is when you have both zeros come in, you're going to have a 1, and both ones, you're going to have a 0. Similar to here, which you have inputs C, which is set to 1. So when you have both inputs as 1, you're going to have an output of 0, as shown here. And when you have both inputs as 0, you're going to have an input of 1. So your answer should be a NOR gate here. Sorry. N-O-R. A NOR gate should be your answer for that one. Everybody understand this part here? Part 2 that I just do about the NAND gate. Hmm? Good. Excellent. So moving on again now. So now a circuit combines 3 NAND gates. More complex now. So 3 NAND gates together. The inputs of the circuits PQ are shown in figure 10.3. That's here. So they say points R, S, and T in the circuits are labeled here. R, S, and T. Input P is set to 0 and Q is set to 1. So here I'm just going to write it as P is 0 and here is 1. Good. So when you're coming with a 0 and a 0, at the end of the NAND gate, when two zeros come in, you're going to get output of 1. So we're going to trigger it as 1 being here. And here going to be two ones going to come in, you're going to get a 0. You follow me? So now we're going to say determine the logic state 0 or 1 at points R. So at point R, what you're going to be, when two zeros come in, you're going to get an output of 1. When two ones come in at S, you're going to get an output of 0. And for the NAND gate now, in the NAND gate, your NAND gate, which is T, let me go back to the NAND gate. When you have a 1 and a 0 in your NAND gate, a 1 and a 0, what your output going to be? 1. So your answer here should be 1. Everybody okay how we get this thing? So let me go here again. When here is 0 and 0, your output is going to be 1. When here is 1 and 1, your output is going to be 0. So 0 and 1 going to give you an output of 1 as shown here in the diagram. Good? Everyone okay with understanding how we trace the 1 and 0s? Hmm? Good. Nice. So we're moving on now to this one here, which is number 6. We work on IGC, CXC. We could work on you here. This was a 2010 paper. Um, so for the IGC students, we are following up with this. They said this is a truth table of logic gate is shown, for logic gate shown below. So if you notice for the truth table here, you only have 0 when both of your input is 1 here as an A and B. Name the type of truth table that would give here. Once it have a 0, your output is 1, and when both of them is 1, your output is 0. Which gate you think that is? Coming from a lecture here. Which gate you think it is? Hmm? So this is it here. This is a AND gate. Someone is writing on the screen while I'm teaching, and it'll be disappointing that you're doing that while everybody else trying to learn. Not sure if you could stop do it, please. Good. So from our lecture here, they said for the question here, once the input have a zero in it, your output is a one. So the only gate that responds to that is your NAND gate. So the answer for this question here, still the name of the logic gate is something called a NAND gate, which we would have done. A NAND gate is the type of gate that we have. A NAND gate. Good. So your answer for that is NAND gate. Everybody okay how we get the NAND gate? Good. Moving on. So now we have a logic circuit here. So this symbol is an OR symbol and symbol, and this is a NOT gate. Good. So we are going through the process of completing the table here. So you would see. So the first one is A, B, C, D, E. So your E is your final output. C and D comes from these two gates. So A and B is your inputs for C. So if it's an OR gate, OR means, we go back to what OR means. Your OR gate says that you must add them. So it's one plus the other. So A or B, once the input has a 1 in it, you're going to have an output of 1. Produces a high output if any of its input is 1. So we're going back here. So C is the output of A and B. So between A and B, because B is 1, your output is going to be 1. Here it's going to be 1 as well, since A is 1, and because both of them is 1, your output is going to be 1. So it's 0 plus 1 is 1, 1 plus 0 is 0, and 1 plus 1 is 1. Good. So as for C, let's go for D now. D is what? A NOT of B. So it's basically opposite of B. So for B, B's are 1, so you're going to become 0 now. B's are 0, you're going to become a 1, and B's are 1, so it already is 0. So we're going to do the E gate now. The E, which is the output of 0 for when conditions C and E. So it's an AND gate. AND means to multiply. 0 multiplied by 1 is 0. 1 multiplied by 0, between C and D, 1 multiplied by 0 is 0. 1 multiplied by 1 is 1. And 1 multiplied by 0 is 0. Everybody see how to complete the table there? For especially C6 students. Anyone have any issues with the table, completing the table so far? Anyone? Good. All right, so we have completed the truth table here for this. Just pay attention how we speed up solving the table. We look for which one is ones and zeros and try to complete it. Which one more predominant than the other? Good. So this is a CXC passive question. Let's show my marks. You get 1, 4 marks, 9, 9 marks. So we're going back to IGC question or another IGC question, which is taken from 2000 and me and whatever, because I've not seen it. But yeah, this is a past paper question. So figure 8, 8-1. So figure 10 shows the symbol of a logic gate. What type of gate this is? Anybody can tell me? Hmm? You comment on the chat. Good, AND gate, excellent. So this is a AND gate. That's your answer for the AND gate. Draw the symbol for NOR gate. The symbol for NOR gate, I can't draw there. So the symbol you're going to use is this one here. This is your NOR gate. Just pay attention to that. Your NOR gate is this one here. So you're gonna draw that symbol. Alright, here. They say the two inputs of a NAND gate are both low or zero. If the two inputs are both zero, what's gonna happen to a NAND gate? Let me go to a NAND gate. So the NAND gate, our NAND gate, if both inputs are, write down the output state if both inputs of the NAND gate are both low or zero. So when both of them is zero, what happens? You get an output of 1. So your output state should be 1. Good. One input of the NAND gate is low and the other input is high. So 0 and a 1. So when is 0 and a 1 is 1 or 1 and a 0 is 1. So your answer should be 1. This is for a NAND gate, right? Should be a 1. Good, then they say part C of the question here. A logic gate contains a number of components. Circle one of the following that is contained in a logic gate. Which one of them we talk about? The logic gate contains a number of components. Circle, well, this should have been transformer here, TR. I don't know how that come out like that, but whatever. Here should have been TR again, transistor. Here should have been TR again. Which one of these you think is a logic circuit contained in a logic circuit, or logic circuit is contained in it? Let's go back to our notes here earlier. They said logic circuits often form the basis of microprocessor, transistors, and multiplexers. Good. So your answer is transistor. So this should be your answer here, the transistor one. Um, so this should be your answer here. Then so pay attention to that. This should complete that one there. We do going on to the next question. For now, so everybody okay so far with how we're doing in past paper questions? Everyone, any questions? Good. I only see one person responding with the others. Good. Good. Everybody okay so far with how we did the past paper questions? All right. Good. For remember for CXC, is not a big part in the syllabus anymore. However, it do show up from time to time, especially in multiple choice. For IGC, it was a big part as well, but from time to time it show up. And for the past 2 years, it haven't shown up. However, it's still there in the syllabus, so more or less likely it will show up. Good. So we'll take at least a 15 minutes break and come back for to finish these two past paper questions or three past paper questions. Alright, everybody okay with taking a 15 minutes break? Good. So see you back in 7:45. So good. So 7:45, resume class, right? Alright, good. So we're back from break. Everyone, I'm here again. Good. Nice. So we continue now from the break. We're gonna finish up two parts of the question that should carry us to the 8 o'clock, and then close class here. All right. Next we discuss that after. Good. So the question here says in this past paper question, not sure which year it is, but for IGC as usual. 2A part 1 they said figure 11.1 shows the symbol of a logic gate and the truth table, which is an AND gate here. Well, say the name of the gate already, give you the answers anyway. So this is an AND gate. So your answer is an AND gate here. AND gate, sorry. Gonna continue again, which is right. It's a completely true table for the logic gate. What type of gate is this? Anybody have any idea what type of gate is this? No gate, gate excellent. So that's a no gate. So and in the no gate, we're going back to the file. The no gate is as follows. For the no gate, we say that a no gate produces a low output if any of its input is high. So you get a 0 once any of the input is high. So we're going to complete the table now. So once the input is high, you're going to get output as 0. So here your A is 1, so you're going to be at 0. Here your B is 1, so you're going to be at 0. Here your both of them is 1, so your output going to be 0. Everything else going to be 1. So we're going to compare to our table, which is 1 0 0 0. Just as is once you have an input of 1, the output is going to be 0. Alright, so everybody okay so far with this? It's 1 0 0 on no gate. So here now we continuing with this question, which is about this logic circuit. So figure 11.3 shows the system of logic gates used to ensure the security of a strong room of a bank. So this is an AND gate, here's an AND gate, and this is a NOT gate. They are saying the strong room door will only open when the output F is 1. So I'm just going to write it here. Here would be 1 for it to open. Complete the table to show that the logic states A, B, C, D, E when the showroom door can be opened. So our AND gate, if we want your AND to be 1, your both of your inputs have to be 1. So this portion here have to be 1 and here have to be 1. So D must be 1 and E must be 1 from the diagram. Right? So if E have to be 1, what must be at the input of a NOT gate for the output to be 1? Anybody can tell me? What would be C value if I want E to be 1? Anybody can say? Or type? Just type the answer. So our output is 1 here because we know that. Good. So David said 1. 0, sorry. So your answer have to be 0. Good. If you're coming with a 0 and a NOT gate, it becomes a 1. So your output here going to be 1. For your AND gate, your both inputs must be what to give you a 1. We go back to AND gate for you to understand it. For AND gate, your both inputs must be 1 in order for you to get 1. So that means A and B must be 1 and 1. So your A must be 1, your B must be 1 from the diagram, and your C must be 0 because it goes through a NOT gate. This is what they call a NOT gate. So this is a NOT gate. This is a AND gate here, and this is a AND gate as well. Good. So these are all the different types of gate that we have here. And so we know that for your output to be 1, both of your inputs must be 1. For your output to be 1, your input must be 0 in a NOT gate. So for your output to be 1 in an AND gate, both must be 1 here. So we complete the table. Everybody okay with completing this table so far for this question? Good. Nice. We're moving on to this question here now. The question here says figure 8.1. Figure 8.1 is a schematic diagram of a logic circuit controlling a lamp. At A, what type of gate is that at A? What's the name of this gate here? Anybody can tell me? A NOT gate, good. So this is a NOT gate. This one here for B at point B, what type of gate it is? A AND gate, good. Good. So we go in with this here. So the output of the temperature sensor is high or logic 1 when it detects a rise in temperature. So here's 1 because it says 1 when it get a rise in temperature. Good. When it detects rises in temperature. Sorry. So the output of the light sensor is 1 when it detects uh rise in light level. So you get a 1 here as well. Good. Complete the truth table. The lamp is lit at the output when you have a the lamp is lit when the input to the relay has 1. So your answer must be 1 here. Good. So your answer must be 1 at this point here. So if it is an AND gate, your answers for it to actually work going to be a 1 here and a 1 because we know that for the AND gate, both your inputs must be 1. Good. So the input temperature from the sensor must be 1. And if here's a 1 because it passes through AND gate, your light sensor going to be 0. So this is what going to make the light to come on. So the output of E, where's E? The output of E here. That's basically a NOT gate we're dealing with. So the output of A is the NOT gate. So the NOT gate of the light sensor. So we go into the light sensor. NOT means opposite. So if your light sensor is 0, then your output going to be 1. 0, 1, 1, 0. You're going to be 0 as well. Your output B. Where B comes from? B comes from after your gate, which is here. Okay? Which is a combination of A, output A, and your temperature sensor. So that's between this column here and this column here, these two columns. So and your output is an AND gate. In the AND gate, let me go back. In your AND gate, produces a high output if all the outputs are high. So we're looking to see when all of them is 1. When all of them is 1 between the temperature sensor and the output E here. So if here is 1, because here and the second row between two columns here is 1, then the output is going to be 1. Everything else is going to remain as 0 because it is an AND gate. Everybody okay with that so far? Have we completed table? Good. This is state the conditions under which the lamp is lit. Which condition is for the lamp to lit? The lamp is light when it comes on at 1. What must happen? Your light, the conditions. What happens to the light? They say the output of the light is high or logic 1 when it detects a rise in light level. So you're going to have a low level light, um, or you can put it as output light sensor, output light sensor is low because it must be 0. Good. The temperature sensor, the temperature sensor, output of temperature sensor output of temperature sensor must be high, and output of E must be 1. Good. Alright, so that's your answers here. The conditions: the output sensor is low. The output, when we say low, it will be detects a low level light. Output temperature sensor must be high. It detects a rise in temperature and the output must be A. Okay, that's how we get all these conditions here to get a 1. Filter light actually. It has this whole column here. This whole column. That's how we do. Okay. It says suggest why B is connected to a relay rather than directly to the lamp. Alright, if we go back, I just going back to our notes. Why we use a relay in the first place? Anybody have an idea why we use a relay? Because we would have done it. We did components. Um, right, and I would have given it a relay uses a smaller current to activate. So this is what a relay does. I'll just copy and paste in it. So this is a relay. You see it in the chat. Alright, a device that uses a small current to activate an electromagnetic switch that would for a large current to flow to another circuit. So the question is suggest why B is connected to a relay rather than directly to the lamp. Why you think? Basically it is to allow to allow for large amounts of current to flow to the lamp. Good. The if you're going to connect the logic gate directly to the lamp, it would not light because your your logic gates only operate at a very minimal voltage, which is sometimes 5 volts maximum. Lamps usually do operate at 5 volts, they operate at far more than that, which is about 115 volts. Think about the light bulb in your room. We typically operates at 115 volts. So and higher currents than logic gates. Logic gates usually operate at 5 volts, and my maximum I might get a logic gate operating at is 12 volts. Typically, they are bought in electronic stores, which usually range at 5 volts. And you are to connect it to a relay, which could operate at the 5 volts, but could allow a much higher current and much higher voltage for the bulb. Good. So this would be the end of today's class. Well, this lecture repeated here, so no need to kill yourself over it. Um, So anyone have any issues concerning today's class? I know it's first time we're actually doing this with physics, this digital class. Anyone have any problems with it so far, or they okay with class online like this so far? Good. Right. I will be posting the notes prior to the lecture so that everybody could go through. However, most of my other notes might be handwritten. Since I've accustomed teaching this on board, I will try my very best to write it over and send it in a PDF document so you could go through it to peruse it first before we go through it in class online. Good. I'd like if everybody could take all the precautionary measures so that they could be safe from the coronavirus and everybody else to see them in the future once we have quarantine. Um, Also, I would like if you have any questions concerning past papers or whatever we did in class, to post it to me and I could send you a message or solve it. Okay? Alright, so good night everyone. Be safe and take care again and see you all next week around the same time. Any questions again forward to me in the group chat and we could deal with it. Alright? Good night everyone and take care. I'm logging out now, so be safe.